Yeah, hi everyone, thanks for coming. Today we have the final talk in our series on symmetric spaces of non-compact type. And Thomas from the University of Santiago de Compostela will tell us about parabolic subgroup and subalgebras.
Okay, so I'm going to talk about parabolic subgroups and subalgebras, which are certain subgroups of the isometric group of the symmetric space of a symmetric space of non-compact type, which are useful when dealing with isometric actions, because they allow us to, in some way, to extend the actions on certain submanifolds to the whole ambient space. And they act transitively on our space, so it allows us to take a maybe smaller, more manageable group instead of the whole G, or being it the isometry group or a connected component of it, right? So let's recall from the previous talks that in our setting, M is a symmetric space of non-compact type, which we can represent as a quotient of Lie groups, where G, in this case, I will suppose for ease of use that it's just the connected component of the identity of the isometric group of M, which is a semi-simple Lie group. And K is the stabilizer or some base point, or equivalently, a maximal compact subgroup of G. We have our Cartan decomposition of the Lie algebra of G, which is K plus P, where P is an orthogonal subspace to K in G, which, with respect to the Killing form, which we can identify, in fact, with the tangent space to M at this base point. And then we also have the root space decomposition, which consisted on taking a maximal abelian subspace of this P and considering the subspaces G alpha, which were the vectors in G, such that bracketing with some element in H resulted in being like a generalized eigenspace, right? So the bracket of an element in H in A with X is just alpha of H times X, with alpha is a linear functional we call a root. We could define a sense of positivity in this set of roots that we will call sigma in this talk, which consisted on just taking the roots that evaluated at a regular vector resulted in positive real scalars. And associated with this set of simple roots, we could consider as, set of positive roots, we could consider a set of simple roots, which were those that can't be written as a sum of positive roots. Associated with this, we have an Iwasawa composition of our Lie algebra, which is K plus A plus N, where N is just the sum of root spaces with alpha being a positive roots, and this induced the diffeomorphism at the Lie group level. Well, so that's basically all that we will need for introducing like the algebraic definition of what is a parabolic Lie algebra. But first, we will check what is a parabolic subgroup geometrically. For this, we will have to talk about points at infinity of our symmetric space. And what are points at infinity? Points at infinity, we can define them by just taking equivalence classes of geodesics, right? We take two geodesics and we say they are equivalent if its distance is bounded. Basically, they converge at the same point at infinity. We can do this. We how to say it bounded, because I think we can do this for any non-positively simply connected Riemannian manifold. So in the case of Riemannian symmetric spaces of non-compact type, we can see that the points of the boundary, the ideal boundary of M, are just the unit sphere in the tangent space to our symmetric space. This is because every point in the tangent space determines a geodesic, and thus it will determine a class of geodesics. And one can see that any other geodesic has a representative, well, there's a representative in this equivalence class, which is given by a geodesic with initial vector, a unit vector in the tangent space at all. The action of G can be easily extended from our symmetric space to this boundary that we constructed, just by defining the action of the group on a class of a geodesic to be the class of the group acting on the geodesic, which is a geodesic because G is an isometry, and one can see that this is well defined. Thus, we have an action of our original semi-simple Lie group on this set of points at infinity. And we say that a subgroup is parabolic if it is the stabilizer of a point at infinity. Or sometimes it is also accepted that G itself is a parabolic subgroup if we want to work with parabolic subalgebras, because as we will see later, by definition, G, the Lie algebra of G is going to be a parabolic subalgebra. An important fact of this is that parabolic subgroups need not be connected with this definition. Nevertheless, I think this is proven in Everland's book, two parabolic subgroups are equal if and only if its identity components are equal. So sometimes if we want to work with Lie algebras, for example, I think in Napp's and Onishchik's book, and parabolic subgroups are defined as connected subgroups of G. Well, precisely, in fact, the identity components of these parabolic subgroups with the previous definition, and not the whole stabilizer, right? Also,
sorry, can I ask something?
Yep.
Can you go back to that equivalence? I didn't get this last bit. You mean that two parabolic subgroups are equal if their connected components are equal, right?
Yeah.
But if you take a non-connected parabolic subgroup and you take the connected component of it,
yeah,
these are two different subgroups with the same connected component.
Not with the previous definition. So Everlane defines a parabolic subgroup as precisely the whole stabilizer of the point.
Okay.
So you can see that if two stabilizers have the same identity component, then they have to be the same.
Okay, thanks.
Yeah, if not, you could take any discrete, any identity component or covering of that, right?
Yes, that's.
Okay, so yeah, that's why sometimes you see that when an author wants to work with subalgebras, they just define the parabolic subgroups to be these identity components and not the stabilizers at the points at infinity. This also works because one important thing about parabolic subgroups is that they act transitively on the symmetric space. And if the parabolic subgroup acts transitively, its connected component of the identity acts transitively, just as the case of the isometry group of a Riemannian symmetric space, right? This is, well, has a difficult step to prove, but the rest of it is easy to see, because a point at infinity can be represented by a geodesic joining two points. So since G acts transitively on M for any 2 points, P and another one that we might suppose is the origin, we have that P is G times O. And this is the difficult step that I won't prove. That I think it is a result of Borel, but I'm not sure right now. The orbits of G and any compact maximal subgroup of G on the ideal boundary are equal, right? So we can find a point in our stabilizer of the origin such that K times X is G minus 1 times X for some K in K, where X is the point at infinity that is determined by the geodesic passing through O and P. Now GK is in the stabilizer of X because of this previous equation, and one can see that GK times O is just G times O, which is P, and thus we have found a geodesic just sorry, we have found an element in the parabolic subgroup taking O to P.
Can I ask a question?
Yeah.
So do I get it right that here X is a point on the ideal boundary and it's represented by a geodesic passing through O and GO?
Yeah.
Okay. Clear.
And then you just use the fact that G acts on the ideal boundary and K acts on the ideal boundary with the same orbits, which is the difficult part. Then we have that parabolic subgroups act transitively. This follows more easily if you work algebraically with parabolic subgroups from something that we will see later on, which is the Landlands decomposition. But this is the geometric proof. The algebraic proof is viewpoint is a little bit different. Basically, you say that well, you start with complex subalgebra of complex semi-simple algebras, and you say that a subalgebra is parabolic if it contains a Borel subalgebra of this complex semi-simple algebra, right? A Borel subalgebra is just the maximal solvable subalgebra of the complex algebra. For the real case, this is a little bit more complicated. We say that the subalgebra is of a real semi-simple algebra is parabolic if its complexification contains a Borel subalgebra of the complexification of G. Equivalently, you can do it just checking the brackets on the Lie algebra. A subalgebra is parabolic if and only if it contains a subalgebra conjugate to K0 plus A plus M. This is what I was telling you before. We can say that subgroup Q of G is parabolic if it is the normalizer of a parabolic subalgebra of G. So this is how Borel defines it. I really haven't checked if this definition is exactly the same as the one before. I know that they have the same Lie algebras, and I guess he introduces it this way to avoid having it connected as Onishchik and Nabdu. but I haven't found a proof that this is equivalent.
It seems that this definition is slightly more general, because like if you just take stabilizers of one point at the ideal boundary, these would be like maximal parabolic subgroups.
No. So I will talk about this later.
Oh, okay,
All
sorry.
parabolic subgroups are stabilizers of just one point in the
Oh,
ideal
okay,
boundary.
sorry.
I will briefly mention it. It just depends on where the geodesic lies.
Yeah.
It produces different types of subgroups.
Oh, sorry.
So,
sorry for my ignorance.
Yeah. So yeah, I think they just do it to consider the non-connected case. But I am not sure this is equivalent. Anyways, it is true that it has Lie algebra, a parabolic subalgebra, and so another way to define them is just saying that a connected subgroup of G is parabolic if and only if its Lie algebra is a parabolic subalgebra of G. Okay, so we now have this definition, and the first question is, well, can you give me an example of a parabolic subalgebra? So the thing is that they can be constructed from subsets of simple roots in an easy way, and this will provide us with all the conjugacy classes of parabolic subalgebras that are in G. So you have your set of simple roots, and you can take a subset of it. And one defines sigma sub phi, well, a subset phi of simple roots. One defines sigma sub phi to be the roots spanned by this subset of simple roots, which is a root subsystem, in fact, of sigma, the set of simple roots of the algebra. And we can define a criterion of positivity in this subset of simple roots, just saying that the positive roots are those which were already positive in the big set of simple roots. Then we can define two subalgebras, which are L5, which is a reductive subalgebra consisting of G0 and all the root spaces with a root lying on this subsystem, sigma phi. It's easy to see that it is reductive because it's invariant by the Cartan involution. And M phi, which is precisely those positive roots which do not lie in this root subsystem. So, for example, I have here the drawing that Ivan and I think Juanma used the other day, where you have K0 and A. So G0 here in this line. Oh, sorry. Here on the first level, you have points representing the simple root spaces or roots corresponding to simple roots. And then on the second level, you have the roots corresponding to sums of two simple roots. On the third level, roots corresponding to sum of three simple roots, and so on, right? So this, for example, will be the drawing for semi-simple algebra of type A4. And on the lower triangle, you have just the negative roots and the ones that are opposite to the sum of two roots, 3 and 4, respectively. So L5 is just taking the whole G0, so this line here, setting, for example, in this case, two simple roots, and taking the triangle that it is on top of them. It is easy to see that it is a subalgebra because the bracket of G alpha and G beta is in G alpha plus beta. And taking G0 with the alpha doesn't change the root space that you're working with. And if you take alpha and beta in sigma sub phi, then alpha plus beta is in sigma sub phi, or it is not a root because sigma sub phi is a root subsystem. Thus, L phi is a subalgebra. And similarly, one can define M phi to be the positive roots which do not lie in this upper triangle. And similarly, one has that it is a subalgebra because positive, elements of M phi lie in root spaces where the root is has non-zero component in positive roots lying outside of phi, and thus bracketing this will only result in elements with a non-zero component, well, in fact, positive component lying outside of phi. So this must be a subalgebra, right? And the drawing of the whole parabolic subalgebra looks like this. This is because if one takes an element lying in a root space in this span of phi and a positive root which has non-zero component outside of phi, its bracket will have non-zero component outside of phi, positive component outside of phi, and thus bracketing this with this will only result on the roots going up. Thus L phi normalizes M phi, so Q phi, the sum of L phi and M phi, is a subalgebra of G, which is what we call the parabolic subalgebra of G associated with this subset of simple roots. It's easy to see that it is a parabolic subalgebra because, of course, we have K0, we have the whole of A, and we have all the positive roots, right? Because the ones that are in sigma sub phi are in L phi, and the ones that are not are in M phi. So here I have a couple of examples. If one takes the empty set as a subset of simple roots, then L phi is just G0 because this is an empty sum, and M phi is all of the positive roots. So the subalgebra you get is a minimal parabolic subalgebra, which is just K0 plus A plus N. If one takes phi, the whole space of set of simple roots, one gets that L phi is G0 plus all the roots. By the root space decomposition of G, this is all of G. And M phi is just 0. So the parabolic subalgebra is just all of G. That's why we said before that all of G can be considered a parabolic subgroup. And if one takes out a root, the resulting thing is just L phi is all of G0 plus the root spaces of roots with no component in this root that you are taking out. This is here represented by alpha of Hj equals 0, where Hj is the dual vector to alpha sub j. And the roots in N are the elements that have component greater than 1 in this root that you are taking out. And this is a maximal proper subalgebra. Well, why are these standard parabolic subalgebras important? Oh, sorry. I will give an explicit example before. So we are going to see a specific parabolic subalgebra of SLNR. So you can see the Cartan decomposition of SLNR as SOM plus the symmetric matrices of trace 0. A is the diagonal matrices of trace 0. K0 is 0, and N are the strictly upper triangular matrices. And if one computes the root spaces, the parabolic subalgebra corresponding to taking out the last root from the root space, from the set of simple roots, will be L phi, the matrices, the block matrices with an n by n matrix, and here lambda with trace 0, which is isomorphic to SL n minus 1 error plus error. And the n phi, the nilpotent part of this decomposition, is just the matrices where we have a 0 here and here a vector of Rn with the corresponding bracket of matrices. And thus our parabolic subalgebra consists of all matrices, block matrices, with where you have an n by n, n minus 1, a minus 1 block here. You have the last column. It can be varied ones, and then here you have a row of all zeros except the last entry, and they have trace 0 because they are in SL and R. So you know now, for example, that this has to act transitively on SL and R mod SON. Well, why are these standard parabolic subalgebras important? Because you have a theorem by Borrelentits, which tells you that any parabolic subalgebra, no matter how complicated it gets, is conjugated to one of these standard parabolic subalgebras associated with a subset of simple root. And in fact, if two parabolic subalgebras are the same for two different subsets of two subsets of simple roots, the subsets have to coincide. So there are as many parabolic conjugacy classes of parabolic subalgebras as there are subsets of simple roots, right? So thus we have that when working up to conjugacy, such is the case when studying isometric actions up to orbit equivalence, it is enough to study standard parabolic subalgebras. Well, with the previous decomposition, one might have some problems, which is that if you think the n phi, if you want the n phi to be the kind of the Lie algebra of a symmetric space of lower rank, because if you check this subset of root spaces, it looks kind of the root space composition of a symmetric space. You have too much stuff in A. So the way to deal with this is to define this A phi as the intersection of the kernels of all the simple roots in our subset, and define n phi to be L phi minus this simple roots. Minus this subspace. One can think of this as taking out the roots that, the roots that don't correspond to simple roots here. Well, pardon me. It turns out that L phi is just the normalizer or the centralizer, the concept of this subspace A phi. And if you take the complementary, the orthogonal complementary to this A phi in A, which is just n phi intersected with A, it is the sum of the span of the 12 vectors, two simple roots in phi, which we call is super phi. It turns out that n phi is still stable under the Cartan involution, so it is reductive, and it normalizes A phi plus n phi. Thus, we can write a decomposition of our standard parabolic subalgebra as precisely n phi plus A phi plus n phi, which is known as the Landlands decomposition. as of the parabolic subalgebra. For example, coming back to the example before, if you take the last root out of SLNR, you have that n phi is just SL n-1 over embedded in SL of n in this way. So you put SL n-1 over in the upper corner of our matrices. N phi is still the same. So the matrices which have a last column of numbers where the last one is 0. And A phi has to be R because it's a one-dimensional abelian subspace. Okay, so now we have this decomposition on the Lie algebra level, and we want to do something similar to what we did with the Iwasawa composition. We know that Q phi acts transitively on our manifold, so we want to get a similar decomposition for Q phi in terms of Lie groups with Lie algebras n phi, A phi, and n phi. So for this is a little bit complicated for the case that we are accepting non-connected parabolic subgroups. There's no problem with the A phi and n phi. You can define them just as the exponentials of the A phi and n phi. And they are simply connected closed subalgebras with Lie algebras, the corresponding ones. But if you want to accept non-connected parabolic subgroups, it gets a little bit more complicated. You have to define n phi sub-0 to be the connected subgroup of G with Lie algebra n phi. There's no problem with this. If you are saying that parabolic subgroups are connected, then you just take n phi disconnected component. But if you want to accept non-connected parabolic subgroups, you have to define K phi to be the centralizer in G of this Lie algebra A phi. Sorry, here it should say the centralizer in K of this Lie algebra A phi. So what will correspond to the projections into K of the root spaces lying in this span of our simple roots, and then define n phi as the subgroup of G generated by taking possible products of these elements in K phi and n phi sub-0. And as one can see, as this the elements of the Lie algebra of K phi are all in root spaces, well, in sums of root spaces of roots lying in this sigma sub phi. And these root spaces are already all in n phi, that the Lie algebra of n phi is just n phi. So yeah, this is...
Sorry, can I ask a question?
Yeah.
So K phi is finite here, right?
I don't think so.
It's discrete.
Nope, it's maximal compact, right? So, yeah, in fact, yeah, you can see it's
but
a maximal
then
compact
it's
subgroup
really strange that the Lie algebra is still the same as the Lie algebra of the connected component, right? Or it's not?
Because brackets of K phi and n phi always lie in n phi.
Ah, okay, I see. Okay.
Yeah. this is because if you take something in K phi, it's a projection onto K of a sum of roots lying in root spaces where the roots are generated by phi, and them can be in the whole of G, but they are also in root spaces where the roots are generated by phi. So if you take brackets with that, it's either in K phi or it is in the projection of the root spaces onto P of the root spaces generated by these roots in this subset.
Okay, thanks.
It has the Lie algebra that we want, and then for the definition of the parabolic subgroup, one can see that one can define L phi as the direct product of A phi and N phi, which is a closest subgroup of G, with Lie algebra the one that we want, L phi, and we can see that L phi normalizes N phi. Thus, Q phi is a subgroup of G, and in fact is a parabolic subgroup, which we call the parabolic subgroup of G associated with phi. And one can see that this multiplication n phi plus a phi plus n phi, which takes m a n into m times a times m, is an analytic diffeomorphism, just like in the Iwasawa decomposition, which is known as the Landlands composition of Q phi. So we know that our parabolic subgroup acts transitively on the whole symmetric space. So we kind of want to get a decomposition of the symmetric space, just like the solvable model that we got when we considered the Iwasawa composition, but by quotienting by K sub phi, that is as a maximal compact subgroup of Q sub phi, instead of quotienting by all of K. So for this, I will talk about boundary components, which are basically the best submanifolds that I think you could consider in a symmetric space of non-compact type. So consider B phi just the projection onto P of this N phi, which is a Lie triple system. And consider the corresponding orbit of N phi in O. Since P phi is a Lie triple system, P phi in upper letters is a totally geodesic submanifold. And if we write S phi as the bracket of B phi with itself plus B phi, and S phi the corresponding connected subgroup of G, it turns out that S phi is the isometry group of B phi, and it is a semi-simple group. And we can either write B phi our this bounded component space as N phi quotient K5, or S phi quotient S phi intersected with K phi. And since it is a quotient of a semi-simple Lie group by a maximal compact subgroup of this Lie group, this B phi is a symmetric space of non-compact type. Moreover, this decomposition that we wrote before as B phi bracket with itself plus B phi is a Cartan decomposition of the semi-simple Lie algebra S phi. And in fact, A super phi, so the part of A in our Lie group that corresponded to the simple roots that we are taking to construct the parabolic subalgebra is maximal abelian in B phi. And more than that, roots of S phi are nothing more than restricting the roots of G lying in this span of the simple roots to our maximal abelian subspace. And the corresponding root spaces are in fact the same. So imagine alpha is a root of G lying in this sigma sub phi. Then alpha restricted to S super phi will be a root of S phi. And the corresponding root space S phi sub alpha will be just G sub alpha. So the algebra basically splits as nice as one can ask with respect to the root space composition of G. One can see this just by just considering the linking diagram of our original root, symmetric space, where we think the nodes here with some certain weight given by the dimension of the root spaces. One takes the subgraph corresponding to just taking the simple roots lying in this phi and taking all the nodes connecting them and asking themselves what is the symmetric space corresponding to this subgraph here, where the weights matter, of course, and how can we embed it in our original symmetric space in such a way that it is totally geodesic and the root space decomposition coincides, right? Well, once we have that, it is very easy to construct an analog of the solvable Lie group model for the Iwasawa decomposition of the symmetric space. But here, the thing is a little bit more complicated for because we will have a product here. So m phi times a phi times m phi into q phi, the multiplication map, was an analytic diffeomorphism. And q phi acts transitively on M. K phi was a maximal compact subgroup of M phi. So quotienting everything by K phi, it will induce an analytic diffeomorphism between M phi, A phi, and B phi, which is precisely M phi mod K phi, into Q phi mod K phi, which is just all of them. And the thing is that this is saying that taking a point in M is equivalent to just taking a point in B phi, which is just an orbit of, an element in the orbit of M phi of O. So here you have B phi, you have O, and you can represent any point in B phi as the orbit of, well, as an action of an M in M phi times O. And then you have to give a point in N and a point in A5, and this determines the group of the symmetric space in a one-to-one correspondence. And this is what is known as the horospherical decomposition of M relative to B phi. In fact, I forgot to mention it earlier. This rank of B phi, since the roots of its isometric algebra are just restricting the roots of G to this other maximal abelian subspace, the roots of sigma sub phi, the rank of this V phi is just precisely the cardinality of the subset of simple roots that we are thinking. And lastly, I wanted to mention briefly how this cardinality of these sets is related with maximal or minimal parabolic groups. So basically, there's this equivalence between classes of geodesics, and if you want to say it, types of simple roots. So, well, maybe it will be better here. Let me. Right. So, oops. Imagine here you have your, well, I will write in 2 dimensions. Sorry, not if I just A. And here you draw the width chambers, right? So D1, D2, D3. This is all. And if you take the analog of this in P, this determines a geodesic. So if the point is in the interior of a width chamber, the geodesic that it determines is called, well, it is the point is called a regular point, and the geodesic it determines will go to a point of infinity, such that the corresponding parabolic subgroup or subalgebra is minimal. So that's it. It's just the normalizer, if you want, of some subalgebra conjugated to K0 plus A plus N. If you take an element precisely on the boundary of 2 wide chambers, the geodesic this determines will go to, well, okay, here I will put rank of B phi equals 0. So the corresponding boundary component is just a point. If you take a point in the intersection, well, of 2, or in the boundary of 2 width chambers, here the rank of the corresponding boundary component associated with this parabolic subgroup will be 1. Same if you have a point in the boundary of 3 different width chambers, you will have a boundary yeah, so parabolic subgroup corresponding to taking a subset of 2 roots from the set of simple roots, and etc. etc. So yeah, with this I'm basically done. So if you want to ask any questions.
Yeah, thanks, Thomas. Yeah, any questions? I got one. Can you share the screen again?
Oh, yeah. Sorry.
Can you go to the slide where you define the boundary component? Yeah.
Yep.
How do you show that S phi, which you defined as, so you take this small b phi, which is the Lie triple system, and then you generate a subalgebra by it, and then you take the corresponding connected subgroup, right?
Yeah.
How do you show that S phi is precisely the connected component of the isometric group of the boundary component? Because I, in general, can only show that it's like maybe some covering of it.
Yeah, it might be some covering.
Oh,
yeah.
okay.
Well, sorry, if it is connected. Well, yeah, it might be so yeah, a covering. Sorry.
Mm-hmm.
Yeah.
So they coincide on like the Lie algebra level, but there might be some.
Yeah. Totally.
Okay.
Yeah, I think you can. Well, I think you did it. Your paper on.
Yeah, but I don't know the answer.
Yeah.
It might happen that it's always like actually
I messed
the
up here.
isometric.
Yeah.
Okay.
I have also a proof, I think, using transvections.
Okay.
Yeah. So.
All right. Thanks. Yeah. Does anyone have any other questions?
Yes. Do parabolic subgroups together, of course, with a symmetry group, do exhaust all the possible subgroups of the isometric group which act transitively on a given symmetric space of non-compact type?
I don't think so, right? Because parabolic subgroups are.
But for instance,
Wait, no, it's of course not true because AN acts transitively and AN is not.
Acts transitively and it's not a parabolic subgroup. Yeah.
Yeah.
Right.
Yeah. So how? So would it be possible to get a complete list of all the subgroups which are acting transitively on a given symmetric space of non-compact type?
You can maybe take like the maximal subgroup of your transitive group, the maximum proper subgroup of your transitive group.
The maximal, sorry?
So you start with something transitive, right?
Yeah.
Say H, and then you take the maximal proper subgroup containing H.
Mm-hmm.
By the result of Mosto, it will either be reductive, which is non-possible because reductive subgroups cannot act transitively.
Yeah.
So it will be parabolic. So basically, you just need to look for subalgebras of a parabolic subalgebra Q phi, whose projection onto P is the whole P.
Yeah.
It's not a list still, but it's kind of like one step maybe.
Because I mean, you know that your subgroup is contained in a parabolic subgroup.
Yeah. That's
with this
very clear. That's what Ivan said.
But,
yeah. This
but
is really
you could have something in between, right?
Yeah.
Just
that's right.
Rather by something discrete or something like that.
Yeah, but I didn't understand what Ivan. Yeah, that's the last bit. What do you have to check? What was
but I mean, you're at the end of the day, you're looking for subalgebras of Q phi.
Yeah.
Whose projection onto the P summoned is the whole P summoned.
Is the whole P.
Yeah.
Okay.
But I don't think it's still straightforward.
But even that's only for connected groups acting.
Yeah. I mean, at least.
Just for connected. Just for connected.
Yeah.
So like, I think in the N phi summon, you have to take N phi and probably A phi as well. But then you can take something in between just the nilpotent part of M phi and the whole M phi.
Yeah, I see. Yeah. Like yeah, it makes sense.
Yeah, I mean, I would say any subalgebra containing minimal parabolic subalgebra also acts transitively. So
yes.
Anything containing K0 plus A plus N acts transitively, basically because it contains A plus N.
Yeah, that's clear.
Yeah, but by definition, anything that contains K0 plus A plus N is something of the sort of the form
yeah, true.
Q phi.
Yeah, that will be interesting to see if it's possible, because I don't really think it's studied, this question, because
yeah,
it's, at least in the compact case, I believe it has been studied, and maybe
yeah. Well, in the compact case, it must follow from the Dynkin's or Mostow's classification of all subgroups of compact semi-simple Lie groups, right?
Yeah. But I'm not sure, because, but for instance, it's well known, this result by Borel, of groups acting transitively on spheres, and also this well-known result by Onishik, that I think we talk about this one day, Ivan, in symmetric spaces of rank 1 and compact type. Then there are also some symmetric spaces with non-expected groups acting transitively, like this CPM